So I want to first thank the organizers for the invitation, and it's a great pleasure to be here presenting this work. So this is I'll tell you about the gravitational wave symphony from oscillating spectator scalar fields and its interesting implication for dark matter physics and beyond. This is a work done with Pankaj Saha and Evangelos Sfakianikis. The work is recently accepted by PRL. So as we know, recently LIGO Virgo discovered the transient gravitational wave signal from black hole mergers. And this marked a new era of observational astronomy and also provided us a brand new tool for probing new particle physics and cosmology. And then just this past year, pulsar timing experiments identified compelling evidence of another type of gravitational wave signal, the so-called stochastic gravitational wave background. This could arise as an echo from very early universe, originated from particle physics, new particle physics, or cosmology, or it could be of astrophysical origin from supermassive black holes. In any case, we see that this is really an exciting time for us to explore the potential of new physics discovery, possibly related to dark matter and even beyond, through the lens of gravitational waves. So there have been a few well-motivated and well-studied sources of stochastic gravitational wave background. Let me just say that the focus of this talk will center around the cosmological source for stochastic gravitational wave background. So another well-motivated yet relatively less extensively studied source for SGWB is parametric resonance during the oscillation of scalar fields in the early universe. Among the existing literature on this topic, mostly they focus on specific cases, in particular related to the inflationary preheating. Then due to the constraints related to inflation, the gravitational wave signal that's predicted is typically out of range for near-term discovery. Either the frequency predicted is too high or the amplitude of the signal is too small to be detected. So of course there are exceptions. For instance, if you invoke the axion gauge couplings as explored by some of the recent work, including another work with my collaborators. So the objective of this work I'm presenting to you today is to conduct a systematic study of generic possibility of spectator scalar fields as a source of stochastic gravitational wave background, identify the scenarios where the gravity wave signal is observable, and explore the associated phenomenology related to dark matter and beyond. So let me first introduce you to some basic concepts related to this study. Spectator scalar fields are scalar fields that are lighter than the Hubble scale at the time of inflation and is a subleading energy component during inflation. So this type of particle or field generically present motivated in beyond standard particle physics framework. It could even be the standard model Higgs, or could be axion or non-axion type of dark matter. So a natural interesting feature of this type of field is that they can typically develop a large initial field displacement away from the true vacuum due to the fluctuation in the de Sitter space during inflation, and is proportional to the Hubble scale during inflation. Or it could simply be set by the initial condition, just like what happens for the inflaton during the slower inflation models. So in our study, it's a phenomenology-oriented study. So we treat the initial phi value as a free parameter. And this kind of scalar fields, they would, the scalar condensate store energy. So it can have potentially cosmological significance. So after the initial displacement, in general, the field would start to roll down at some point and start to oscillate around the true vacuum. If these are free scalar fields, then it's just coherent oscillation, homogeneous all through. But things get more interesting if we consider there could be interaction among the scalar fields, which is a quite generic possibilities. And in this case, during the oscillation, the interaction can potentially activate the so-called parametric resonance phenomenon. This is an area of rapid particle production, and eventually would result in fragmentation of the scalar condensates and triggers gravitational wave production. So for those of you who are not familiar with this parametric resonance, let me first warm you up through a simple toy model example, which is a prototype of the cosmological context that we'll explore here. So the simple model would just, we can consider a harmonic oscillator as equation of motion here, but the difference from the familiar case is that the frequency itself actually also oscillates with the frequency omega. So this alpha cosine omega t part, you later see that it directly corresponds to the interaction effect for the scalar fields in the cosmological context. So what we see by solving this simple system, we'll see that when this omega, the varying frequency of the frequency itself, is close to about twice the omega 0, the amplitude of this oscillation can exponentially grow over time. So essentially, you find some solution like this, where you have this mu, which can be real and positive. So this is the so-called parametric instability. We'll see this mu parameter later, which gets an official name called the Floquet exponent. So parametric resonance essentially means this exponentially growing solution. And this gets its name because there's a dependence on the time-varying parameter, in this case omega 0. In real life, we see a simple example. If you have a pendulum with a length of L that's oscillating in time, which means that this frequency oscillating in time, then you would get this kind of phenomena. Now we come back to our cosmological context. I will first walk you through the parametric resonance in the cosmological context based on one of the benchmark model we consider. This is a two-scalar system where we have this phi, which is a coherent scalar that oscillates, and then it couples to another field chi, scalar field chi, through this mixed quartic coupling term. So the essential dynamics here is that there's quantum particle quantum production of the chi particle in the presence of this time-dependent classical background of the phi field that was initially displaced at the phi 0 or phi initial, and then oscillate at some point. So here, to solve this system, we first write down the equation of motion for the scalar fields in the FRW background. Then for simplicity, we consider that the background field value of the chi field is 0, and then its fluctuation is delta chi, and then we can decompose it into Fourier modes for the study. Then we find that the mode function for the chi field its evolution would satisfy so-called Hill-Matthew equation. As you see here, this should remind you of this toy model that we walked through earlier. You have the frequency, and the frequency itself actually oscillates because it depends on the field value of phi that oscillates around a true vacuum. So the parametric, as we have seen, this type of equation will have a parametric growth solution, meaning it has this exponential growing behavior, and it depends on the parameters, the momentum of the mode, and this Q, the resonance parameter, that depends on the coupling, the initial field value, and the mass. Yeah, as I already mentioned, this type of equation has this growing solution with this mu called a Floquet exponent. So we can visualize the resonance region in the Q K-square plane, or you can also visualize it in terms of the evolution of parametric resonance in terms of chi field or its number density evolution in time. So later on, during this parametric resonance era, we enter the nonlinear regime. This is where the produced quanta, the chi particle, grows and grows, and then finally the back reaction or the rescatter become important. And then this will drive the particle production process to an end in the context of preheating. This means shut down the preheating. So eventually, the originally homogeneous condensate of the phi field would fragment and then source the gravitational waves. So these are the show you how we incorporate the back reaction in the calculation. So that is a general important aspects of parametric resonance based on one of our benchmark models. So in our study, we considered 4 simple renormalizable models. So I'm using the particle physics language here. And we cover both the massive and the massless scenario. For the massive case, we scan over a wide range of mass for the numerical analysis. So here we have the model A, which is essentially the model I've shown you. You have a mixed quartic coupling. And the model B, we have this trilinear coupling between the 2 fields. Model C is a self-coupling case. And model D, we have both self-coupling and mixed quartic coupling that couple the 2 fields. So now to show you the overall history of the evolution of this type of scalar fields. So first, as I have mentioned, at the end of inflation, initial displacement of the phi field was set in, and it's frozen there for a long time, until at some point where the Hubble, as the universe cools down, the Hubble drops to be comparable to the mass scale of the phi field itself. Then at this point, the scalar field starts to roll down and oscillate around the true minimum. So even for the massless case, you can write down the effective mass term. So this is the era of the parametric resonance and gravitational wave production. Then in our study, for simplicity, we assume a radiation domination throughout the time range of our interest. That means the phi would be the subleading energy component, and we parameterize the fraction of its energy in the total background, alpha, as a free parameter. It depends on the initial field displacement. So the final fate of the scalar fields, what about the ultimate outcome of these fields? So there are a couple of possibilities. So after the particle production ends, this phi and chi fields can decay to the standard model through other couplings that are not included in our minimal framework, but can be incorporated and would not affect the main results. Alternatively, if the scalar fields are cosmologically stable, they could constitute radical dark matter or dark radiation that we can probe through like CMB dot and effective, that we have heard a lot in today's talks. So this would be very interesting phenomenology that's complementary to the gravitational wave signal, which is the main target here. I will discuss more about dark matter, dark radiation shortly. So now come back to discuss more about the central analysis here that is about gravitational wave signal. As I have previewed for you, and let me re-emphasize here, is that the gravitational wave signal arises here because parametric resonance drives the rapid particle production era, and that leads to large time-dependent field inhomogeneities, which satisfy the general criteria for gravitational wave production. So before getting into detailed calculation, there are some rule of thumb for gravity wave background from peak sources, as demonstrated by these people. So essentially, so this formula, there are a number of parameters here. I'm not going to delve into detail, but there are a couple of key points I want to take notes on. First, the peak frequency of the gravity wave signal is determined by roughly the Hubble scale when this process happened. Either you can apply to the phase transition or during the parametric resonance era. And then you multiply that by the redshift factor. And then in regard to the peak amplitude of the gravity wave signal, it has various parameters here. One important thing is this alpha dependence, which I have defined earlier. The alpha is a fraction of the source of the gravitational wave energy in the total cosmic energy background. In this case, how much is stored in the oscillating scalar fields. Okay, so these are the rule of thumb to give us some ballpark estimate. But of course, to get accurate results and be able to draw the spectrum for the prediction, we need to do the numerical calculation. So here we write down the equation motion for the source scalar fields and how they affect the Hubble. Then gravitational waves would arise as the transverse and traceless part of the metric perturbation sourced by the anisotropic stress of these scalar fields. As its equation motion is shown there. Then further, we will derive the gravitational wave energy, the rho GW, based on the H that we have, the metric perturbation we have computed. Then finally, to come to the observables, the gravitational wave energy density spectrum omega GW as a function of K or the frequency can be constructed based on what we have obtained early on. So what we ultimately did is to solve this system of the equations, including this tensor perturbation equation for the gravity waves. In a radiation-dominated background on lattice, we use a cosmolattice in particular. So here's a money plot. So I will show you the models and the underlying parameters in the next slide. But the main take-home message is that, so here are the experimental sensitivities, and here are our predictions, these colorful different style lines. So the main message here is that from this rather simple and generic scenario, the predicted gravitational wave signal can be detectable by a wide range of gravitational wave detector, from the range of PTA to LIGO Einstein telescope, Cosmic Explorer, this 10 to 100 Hertz range. So now let me show you what are the underlying models. So just to remind you, these are the models I've presented to you earlier. And here are the model parameters that correspond to the benchmark, those signal spectrum that I've shown you in the last slide. So the important message here is that we see a wide range of gravitational wave frequency that we can predict here actually correspond to a wide range of a new physics energy scale that's behind it. For instance, if you see the phi mass of 10 to the minus 13 eV corresponds to a nanohertz, well, close to GeV, you get to like 100 hertz in terms of gravitational waves. So as I'll emphasize, discuss more in the next slide, particularly here we can see a potential dark matter candidates will simultaneously address the recent PTA findings. Yeah, so how does dark matter arise from this scenario? So essentially, while this phi field oscillates and depletes itself through particle productions, it may not be fully gone by the end of the parametric resonance. So then the residual phi, if it's massive and stable, can serve as dark matter candidate, where the relative density is predicted as following. So the benchmark here we found is that with 10 to the order 10 to the minus 13 eV mass, we can it can give rise to nanohertz gravitational wave signal and with a detectable amplitude. So we see here is that we have potentially viable dark matter candidates will simultaneously address the recent PTA observation. And from another perspective, here we see a novel discovery channel for ultralight dark matter that was not previously studied or emphasized. Okay, so we also, let me just quickly go through some other complementary prediction in terms of phenomenology from this scenario. So first, there are various sources of potential contribution to delta N effective. So first, the gravitational wave itself is a form dark radiation, so you think it can contribute to delta N effective. So we estimate this potential contribution and found it's just too small, would generally be non-detectable. But we also have other sources from some of the models. We have the massless scalar fields, then themselves can contribute to delta N effective. So we estimate both through the analytical estimate and also did the numerical check. So essentially, if you have order 10% of this energy fraction, you lead to order 0.1 delta N effective. Then if you have a smaller fraction, then it's even safer. So generally, it's safe in regard to the CMB bound on delta N effective, well, can be detectable with upcoming CMB observations. Another thing that you may concern is that this kind of scalar spectator, their fluctuations are in general uncorrelated with a standard perturbation generated during inflation. So there may be isocurvature constraints. So we look into the isocurvature constraints from this model. The field, the energy perturbation depends on the field fluctuation, which is hi over 2 pi in this kind of model. And energy density depends on the initial field value. Yeah, I'll and in a minute. And the initial field value, as we found, is close to the M Planck, favored by the detectable gravity wave signal. So we plugged all this into the CMB constraints on the isocurvature. We find that it's essentially imposed a constraint on the the Hubble during inflation to be 10 to the 13 GeV over F, where the F is smaller than 1 parameter. So this is, as you see, is comparable or even weaker than what we already know from the tensor to scalar ratio constraint on HI. So it does not impose further restriction on the model. So now let me come to conclusion. In this talk, I've shown you that oscillating spectator scalar fields is rather general, rather generically present in the early universe. It's a really simple system, the natural source for gravitational wave background. We analyzed benchmark models and their gravitational wave signal and found that a wide range of detectable gravity waves can arise from this scenario. In particular, we also found there can be viable dark matter candidates that simultaneously address PTA observations with a correlated CMB signal in form delta N effective. Then, just to mention that there's a work in progress that we're considering analogous system with complex scalar fields that can lead to low-scale F-like-Dyne baryogenesis model, which is a way to address the matter-antimatter asymmetry puzzle. And this scenario also can lead to detectable gravitational waves with novel complementary searches with terrestrial experiments probing GeV scale new physics or lower. So yeah, so this is the end of my talk. I have another slide, but I think I'll just end the talk and thank you. Yeah.
Thank you.